Welcome back. We are at lecture 53. We have started integration by parts. Got a pretty good start on it. We've got a couple of problems that we probably ought to look at. We are rounding out to kind of the end of sections to cover for this course. If we don't do anything justice this semester, there is a kind of a natural overlap in the start of 241 comparing it to the end of 141. So you will look at probably sections 5, 7, which we're going to get a little bit of a start with today, and 5, 8. Those would be the first two things you look at in 241. So it does kind of pick up where we leave off, but not exactly. There's a built-in overlap because we never really know in all the 141s the depth to which those sections are covered, because they are at the end of the semester, and everybody trying to get stuff in at the end of the semester. But if there's anything that doesn't quite click 100% from the latter two sections that we cover, 5, 7 and 5, 8, then that's where 241 begins. But I'd like for it to click this semester. That'd be nice. So integration by parts. Let's continue with this. We've got a couple of examples where it doesn't seem like we have enough in the integrand to choose from. So let's take a look at these. We had a natural log yesterday in a problem, but it also had an x in there too. I think this was our last problem yesterday. X times the natural log of x. But what if there's just two things in the integrand, and we've got to identify each of those things, one of them as u and the other as dv, right? There are two things. Just to review here. We want to identify the two pieces of the integrand, part of it, because it's by parts, as u and the rest of it as dv. So if we can do that, and it's going to work, then it breaks down or gives us this new problem. This is not a problem because it's finished, but this is the next integral that we have to visit, is v du. Maybe that's a little better, easier. Some reason it's integrable and the original problem was not. So if this is where we're headed, part of this has to be u and part of it has to be dv. This is almost a no-brainer. What is u? Okay, because there's no way u could be dx. So dv has to be dx. So in this problem, we're going to let u equal natural log of x. Derivative of v would be dx. Everybody see that that's the only decision we can make on this problem? So if you've got two pieces and one of the pieces is dx, dx has got to be dv. And if it's going to work by this method, hopefully when we do this, with this v du will be something that we can integrate. I guess I should have started with this. What we're really searching for is something such that when we take the derivative of that, we get natural log. We don't know anything like that. So we don't have a choice but to use some other method. Substitution's not going to work. So if it's going to be integrated in this fashion, it's got to be this particular choice for u and dv. Derivative of u is 1 over x dx. If the derivative of v is dx, what's v?
0. Constant?
Would be 1.
Why?
1x, right?
Oh.
So the derivative of v would be dv, derivative of x would be dx. So if it works, I think it's going to, it's going to be uv Don't ever worry about what u and v are, just write them down. This next piece tells us if it's going to work. It's v times du. There's v, du is 1 over x, dx. Is this going to work?
Yeah.
It's going to work. Because we can combine x times 1 over x So x times 1 over x is 1. And the integral of 1 integrated with respect to x is x plus c. So it is integrable. So if we're looking for something that you can take the derivative of and get natural log of x, not that we want to remember this. We've got all kinds of other things we need to remember, but there's the function that you can take the derivative of and get natural log of x. So if you don't trust that as the answer to this integration problem, take the derivative of this answer and you'll be right back here. Question on that? All right, next one has inverse trig in it. This is an example in your book, and I think it's worth looking at, even though you have it in your book as an example. So what's the only logical, well, not logical, what's the only realistic choice? U is inverse tangent, and dv is dx. Derivative of u, derivative of inverse tangent. Yep. And if the derivative of v is dx, then v must be x. So is it going to work? uv inverse tangent x times v, which is x, v times du. That's not quite as obvious when we get to this step. As much as that looks like an inverse tangent integrand, it is not an inverse tangent integrand. Any suggestions? What? It is integrable, and we have done this kind of problem repeatedly.
If you pull the edges out.
Make it a natural log format. So if it's going to be a natural log format, this is going to be our u, right? We're going to do a substitution now. Let u represent 1 plus x squared. du is 2x dx. Any corrections needed on this integrand?
1/2 in
Okay,
front of
we
it.
need a 2 and a 1/2 in front. So what is this entire numerator? 2x dx is du. And this denominator is what we chose to let represent u. So this is du over u. And as Kent said, that is natural log, right? Du over u. Or if you don't like that, that's the same thing as 1 over u, du, which is natural log. So we're stuck with this little 1/2 out in front. We're integrating du over u, which is natural log of u. I'm not going to write u down. I'm going to write what u was represented, which is 1 plus x squared. Do I need absolute value?
No.
Don't need it, because 1 plus x squared is positive. So the reason why I think this is a valuable problem to look at, that may not look integrable when you first look at it, but if you'll try some different thought processes in your mind, and the first of which might be inverse tangent, but that x kind of keeps it from working. Whenever the degree of the numerator is 1 less than the denominator, it's got a good shot at being a natural log integrand.
If we wouldn't have thought to do that, would it have worked to do the u and v thing again?
I don't want to say that it won't work. It won't work quite as easily with this as basically being one step.
Okay.
But what concerns me is that we might end up right back here where we started with that, trying to integrate this one by parts. We might end up with an inverse tangent integrand again. I'd have to try that to make sure. I know it works this way. If I did it by parts, I don't know. Can't answer for sure. Questions on that? Let's do a little bit more with that right there so that if we don't have it exactly in that form, that we still feel like we can handle the problem. Questions about this before it goes away? So if we see 1 over 1 plus x squared dx, we know that is
An inverse.
arctangent or inverse tangent of x. But what if we don't see it exactly in that form? Point out where this is.
You can always substitute in, like that problem yesterday that had x to the 4.
You're going to see other possible versions of this where they end up converting into this form, where you've got some u, like maybe, I don't know, was it x squared or t squared? Something squared squared we had in a problem yesterday. And then you can also show that you have the derivative of that thing there. So as long as those things are in agreement, it's the same formula. But what I'm thinking about right now is suppose that's not 1. Suppose that's some other number. Suppose it's a squared. Now I'm picking that number knowing that I'm going to end up with an a. So if that number happens to be 5, we know that's not some nice convenient number squared, but it is the square root of 5 squared. So if that's some number other than 1, and this is some variable quantity squared other than a nice clean x, how do we integrate something that looks like that? So let's go through this problem, and then any problem we see that is in this format, we'll kind of be able to jump from the original problem to the final answer without having to redo this each time. So the first thing I would want to do is make this number that occupies this position, make it 1. So how can I make it 1?
Square root and divide it by itself.
Divide by a squared all the way through numerator and denominator. So the numerator becomes 1 over a squared. This term becomes a squared over a squared. And this term becomes u squared over a squared. That's legal, right? To divide the numerator by a squared and divide every term in the denominator by a squared. You're not going to have to replicate this. This is not a test question, but what we're doing is if you're ever given anything like this, you're going to be able to jump directly to the answer because we're doing this all the way through this time. 1 over a squared. A squared's a number. Why don't we just move that out in front? So we've got still 1 and a du. A squared over itself is 1. And u squared over a squared, I'm going to write that as u over a, the quantity squared. Now, is that looking a little bit more like that?
Oh, yeah. Mm-hmm.
It's a little bit more like that. We've got the 1 in that position. We don't have u squared, but we've got u over some number squared. That could be 3x over 5, x plus 7 over 2, some variable piece over some number. So let's let, and I've already used u in this problem, so let's let w equal u over a. What's the derivative of w? A is a number.
1 over a.
1 over a.
U. Use 1 over
du, right? This is like x over 5. So the derivative of x over 5 would be what? 1/5,
Yeah.
right? So if I want to change this problem into this format, where I've got u over a, the quantity squared, that's going to become what? W squared?
Yeah.
Now the question is, do we have dw in the integrand? We've got 1 over 1 plus w squared. That's basically letter perfect. 1 plus 1 over 1 plus u squared. This is the same thing, right? The issue is we've got du and we've got w's in here. Here we've got u's and du's. So we've got to see if we have enough to have dw. Do we? We've got a du. Do we have a 1 over a in the integrand?
No.
We can do that. Let's multiply by 1 over a as long as we... So we're dividing by a as long as we multiply by a. So now the integrand... Run out of space there. Out in front, we have 1 over a squared times a, which is 1 over a. And all this numerator is really what? That's really dw. 1 over a du is 1 times dw. And in the denominator, we've got w squared. That's exactly what we want. That's exactly the inverse tangent integrand. So the answer is 1 over a, not a final answer, but an intermediate answer. And in terms of our original numbers and letters, it's 1 over a inverse tangent of what was w representing temporarily
U over A.
u over a.
Okay.
So that might be something handy to kind of memorize, for lack of a better word. If we have a problem that starts out like this, then you can go directly to this answer without having to do battle with this integrand each and every time. So it might be something as simple as that. Is that exactly an inverse tangent integrand? It isn't, but it is this, right? Where a squared is 3, so if a squared is 3, what's a? Square root of 3. So what would the answer to this be?
Square root of 3.
1 over square root of 3, inverse tangent of x over square root of 3 plus c. We'll move on to the next problem. So you don't have to do that battle all over again. So you might, if you've written one thing down today, probably it would be that to this point in time.
Is the square root of 3 because...
Wait, where did you get square root of
Yeah.
Yeah, I don't get that.
No, I'm not
A
understanding.
becomes
A squared is 3.
A squared becomes A.
Oh,
So
okay.
it gets divided. It gets
So A would be the square root of 3.
Where did you
So it's always 1 over A, so it's 1 over the
Oh.
square root of 3. Inverse tangent of u over A. U is x. U squared is x squared, so u must be x. So x over the square root of 3 plus c. Anything else for that moves?
loses the power. So your answer loses the power. If it's a 3 there, it's going to
All right. Didn't know we would be getting there this soon. Does anybody have a question over an integration by parts problem before we kind of leave that temporarily? If you have one tomorrow, you can ask it. But for the most part, we're going to leave that section behind. and go back in the back of the book to, if I can find it, somewhere in the 50s, I think. Appendix G. So this is on page A50 in the back of the book. Now this is going to kind of pave the way to a technique that we're going to encounter in 5.7 called integration after you decompose a rational function into partial fractions. So we're going to eventually be decomposing an integrand into partial fractions. So that's really the technique. The technique is partial fractions, integration using partial fractions. So this is going to be the simplest thing that we've ever done to this point in time in this course, what I'm going to do right now. So let's suppose you had an algebra problem. This rational term, rational expression, over that. So algebra 1. So here we are in 8th grade, maybe 9th grade. Okay? And you are asked to put those two fractions together into a single fraction. What would you do? Get a common denominator. Okay? And what is the common denominator?
X minus 1.
Okay, their product would work. So if we're going to combine them into a single fraction, we decide on a common denominator. And then basically what do we do to each fraction so that we can combine them?
Multiply the denominator.
Okay, multiply by whichever version of 1 happens to work. So in the first one we want to multiply by x plus 3 over x plus 3, which is 1. And in the second one, we want to multiply by x minus 1 over x minus 1. Now they have the same denominator. Is that correct? And once they have the same denominator, we can combine their numerators. Well, the numerators are 3 times x plus 3 plus negative 5 times x minus 1. Typically, we would distribute, group together like terms, and see what we come up with. So the denominator is set. We could multiply that out, but nothing really is gained by doing that. In the numerator, we've got 3x plus 9 minus 5x, what, plus 5? So what's the numerator? Negative 2x?
4 minus 2x.
Negative 2x plus 14.
Plus 14?
Oh, 14. 14 minus 2x.
So algebra 1, right? Easy problem?
Yes.
Now we're going to do this problem in reverse in this section. We're going to start with something that looks like this. In fact, that's what the integrand is going to look like. Now the denominator may or may not be factored. It's a little bit easier if it is factored. That just saves us a little bit of time. So we're going to be trying to anti-differentiate something that looks like that. So the first thing we're going to do is decompose it into partial fractions. We know what those are for this problem. So I'm not talking about the technique. I'm just talking about why we would want to do this. Didn't we start with those two fractions? Right? And we kind of got a common denominator, multiplied through, grouped together like terms, and we came up with this. So isn't this problem really the same thing as
Can you take the integrand of each of those terms?
yes?
Okay.
And that's the advantage. So we've taken this not ugly, but kind of cumbersome, rational expression, and we've decomposed it into two pieces. Isn't it always easier when things are added as opposed to multiplied and divided? Can't you just integrate the first piece and integrate the second piece and you're done, right? So is everybody convinced that we did the right stuff up here and that this rational fraction is really the sum of these two?
Yes.
So we could integrate that sum by integrating each piece. And my contention is that the answer almost jumps out onto the paper and you hardly have to think about it at all. What is this? We were to integrate 3 over x minus 1. Maybe it doesn't jump out onto the page. It jumps out for me onto the page because I've seen this hundreds and probably thousands of times.
The natural log.
It's a natural log. Okay, aren't both of these natural logs?
Yep.
Isn't the degree of the numerator 1 less than the denominator, right? So since it's not jumping out onto the page, wouldn't you let u equal x minus 1 du is what? 1 dx?
Yes.
So you could slide the 3 out in front, right?
3.
So isn't it 3?
Natural log of x minus 1.
Does that work? Because it ends up being what? Du over u? Which that ought to, let's see if I'm correct here. Doesn't it make the second one jump right out onto the piece of paper?
Minus 5 times natural log of x plus 3.
Plus c. Okay, first one was kind of crawling out onto the paper, and then the second one actually jumped onto the paper.
Oh, yeah.
Much easier to integrate these two things than the original problem?
Mm-hmm.
Absolutely. So if we can take something like this, decompose it into partial fractions. We haven't talked about how we go about doing that, but if we can, we end up with a problem that's a lot easier to integrate by integrating the two pieces as opposed to the original problem. Now, some things that are true about this original problem. The degree of the numerator, which is 1, is less than the degree of the denominator. Degree of the denominator is 2. So if that is not less,
It's improper.
then we will handle that situation later. We need to do some division and get a remainder that is in fact less. But in this problem, that's the first thing I would check. Degree of the numerator 1, degree of the denominator 2. We can use this technique. So let's start with this problem. We know what the answer is going to be, but let's show the technique of how we decompose this into partial fractions. So there's the problem we're handed. The type of factors that are in the denominator, these are linear factors. So when we have linear factors that are not repeated, because we don't have x minus 1, the quantity squared, or x minus 1, the quantity cubed, so we don't have any repetition of the linear factors that are present, then this would be the technique that would work. So off to the side, before we do the integral problem, we do the decomposition problem. So how do we do that? Whenever we have a linear factor in the denominator that's not a repeated linear factor, linear factors will basically command or demand a constant numerator. We don't know what that is when we start this problem. Here's our other linear factor. It will command a constant numerator. That's the way we keep the degree of the numerator less than the degree of the denominator. Because we have a linear denominator, we need a constant numerator. So the task is to find A and B. Well, we find A and B in a similar fashion to what we did on the other problem. Any question about that? Step That's kind of the first step in the decomposition. So we've got this thing on the left side that has a denominator, x minus 1 times x plus 3. What do you think we probably need to do with the right side so we can begin to equate the left side with the right side?
Break it up.
We've already done it. We did it about 5 minutes ago. We need to get a common denominator on the right side. So we need to add these two fractions so we can basically compare the left side to the right side. So we need to multiply by x plus 3 over x plus 3 and x minus 1 over x minus 1. So the numerator is a times x plus 3 plus b times x minus 1 all over the common denominator. Does that work? And we did that with numbers a minute ago. Unfortunately, we have letters now. What's next? Got two fractions that are set equal to each other. Are the denominators equal? Okay, we don't have to do anything with them. In fact, that's why we did what we did, is to make the denominators equal. Now the question is, how is this numerator equal to this numerator? Well, let's multiply it out. We have ax plus 3a, bx minus b. So let's group the x terms together. And how many x's do we have on the right side? We have a plus b of them, right? We have ax here, we have bx here. If we factor in x out, it gives us a plus b. And everything else that doesn't have an x in it must be a constant, right? So all we have are x's and constants. So the 3a and the minus b, since they don't have any x's in them, they must be the constant. Now tell me what must be true if this is indeed an equation. A plus b has to be negative 2. Is that correct? That's what Casey said. And I trust Casey. She's given me good answers all semester long.
Yes.
Okay? Doesn't the coefficient of x have to equal the coefficient of x over here? Left side and right side. So what's the coefficient of x here? Negative 2. It must be equal to the coefficient of x over here, which is a plus b. Seems logical? Tell me another equation.
3a minus b equals 14.
Good. 14, which is the constant on the left side, must be equal to the constant on the right side because these two things are equal. Now, you have two equations in two variables. There's a variety of techniques to solve them. How do you want to go about solving this particular version of two equations in two variables?
Substitution.
Substitution would work.
Solve for a in the first equation.
Solve for a in the first one and plug that in for a in the second one. How about if we line them up?
Since b is positive and negative, those cancel out.
Do you hear what Jonathan said?
Oh,
Because
yeah,
in this
b's
problem,
cancel out.
we have a positive b in the first equation and a negative b in the second. If you line them up, and whatever you call this, linear combination, basically add the two equations together. Now, substitution will also work, and we'll actually probably use that more than this technique. Just we get lucky on this problem because the b's knock out. So if I add the left side of each equation, what do I get?
12.
12. And if I add the two right sides, 4a and the b's drop out.
A plus 3.
So a is 3. And now that we know a and we have some equations that interrelate a and b, So negative 2 is 3 plus b. b is what?
-5.
Negative 5. Do you remember the original problem we had? Wasn't a, the numerator of the first fraction, 3, and b, the numerator of the second fraction, was negative 5. So as soon as you find a and b, then you go back to the original problem. Which we've about done everything we can do with this problem. Now that we found a and b, we go back to our original decomposition. There was our first fraction before we started getting a common denominator. There's our second fraction. So 3 over x minus 1, negative 5 over x plus 3. And if you look back to what we had earlier, that's kind of what we started with. This integrates to a natural log, 3 natural log of x minus 1. This integrates to negative 5 natural log of x plus 3. Does that work? Mm-hmm. That's probably the basic type of decomposition, is we have this kind of ugly, at least cumbersome, rational fraction. We try to break it down into a sum or difference so we can integrate each one of those.
Is your denominator always going to factor like that?
No. And then it falls into a different category. If we have, for example, her question is the denominator always going to factor? When it does, this is our technique. When it doesn't, let's say it's quadratic, then it falls into another category where the factor is an irreducible quadratic, which we approach that a little differently. Okay, this ought to be about the right amount of time. Now, we want to look at a problem that has linear factors in the denominator, but some of them are not just to the first power. They're a linear factor squared or cubed or to the fourth. And you might say, well, that's not a linear factor anymore if it's squared. The factor itself is linear. It's just raised to higher powers. So let's kind of start the way we did the other problem. Let's start with an Algebra 1 problem. There's a linear denominator. Here's the same linear factor, but it's squared. And then we've got some other linear factor. Can we put those three things together into a single fraction? This is not the calculus problem yet. This is the algebra problem that we're going to probably draw more from this process than we drew from the previous problem. If we were to put these together, what would be the common denominator?
X plus 4 cubed.
X plus 4. We don't need a cubed. All we really need is a squared, right? Because this is at its first. This is this factor to the first. This is the same factor to the second. So if we've got it to the second, we can accommodate this one, right? And then the other factor we need is an x minus 2. Now, if that becomes the common denominator, really kind of the least common denominator, how do we deal with these individual three fractions so that we can convert them or add them together into a single fraction? What do I need to multiply the first one by?
X minus 2 plus 4. X minus 4.
Okay, need to multiply by x plus 4 times x minus 2, numerator and denominator. How about the second fraction? It's got the x plus 4 squared, but it needs an x minus 2. And how about the last fraction? X plus 4 squared. Everybody agree that we can put all these together and have a fraction that has this for its denominator? So the numerators, since we now have the same denominator in all three fractions, we can just add the fractions by adding the numerators. plus -1 plus Now let's expand and put everything together in the numerator. So let's multiply these two together. So the first term is x squared. It gets doubled. The middle term is what? Plus 2x, right? And it gets doubled. And the last term is minus 8, which gets doubled, minus 16. We've got a minus x and a plus 2. We're going to square that and then multiply everything by 4. 4x squared. The middle term would be 8x times 4 is 32x. And the last term is 16 times 4 is 64.
Yep.
So how many x squared do we have in the numerator? 2x squared, 6x squared. How many x in the numerator? 35? Is that right? And what is the constant in the numerator?
50.
50 plus 50? So were we able to take the three original fractions, one that had a repeated linear factor in the denominator, and combine them into a single fraction that had the same repeated linear factor in the denominator? We were able to do that. Algebra 1. What's the nature of each of the numerators that we started with in each of these fractions?
One less degree.
It's one less degree. Actually, I guess, than the nature of the factor. But aren't they constants? Every numerator was a constant? Even though this looks like a second degree denominator, it's a linear factor. That's what we look at. The linear factor, anytime you have a linear factor, it will always take a constant numerator. So, if we had the reverse of this problem, could we start with this and work our way back to the three original fractions? If we could, then we could integrate those three pieces a lot easier than we could integrate this. So this is kind of the second part to the linear factor. If you have a repeated linear factor, it also takes a constant for a numerator. So if we're doing this problem, which, if you notice, the fractions that we're starting with are getting uglier, right? The first one was semi-attractive. Actually, probably not. Probably pretty mediocre looking, below average looking. This one's pretty ugly, and we're at really one of the kind of the more basic techniques of decomposing fractions into partial fractions. All right, so I mentioned this before. Let me mention it again. Is the degree of the numerator smaller than the degree of the denominator?
Yes.
Okay, numerator is x squared. What's the degree of the denominator? It's x cubed. So we can decompose it in this fashion. And then back to Katie's question or comment, are we always going to be given this thing where it factors really nicely? No, but sometimes we will. So we'll start with that and then see how we deal with it when it's not factored for us. So here's the decomposition step. We want to start with a constant over the first linear factor, b, another constant, even though it might be the same number, I don't know, but I'll allow for the fact that it might be different, over that same linear factor squared. And if I had that factor cubed, I would have a third factor, c, over that linear factor cubed.
How would you know that one
Okay, I see.
I mean, I know that because we came from a cube, but if I started from this,
Right. What we're doing is we're allowing for, and that's why I like to start this problem the way I started it, we're allowing for the possibility that there's a fraction that had x plus 4, the quantity squared, and a constant numerator. In fact, we know that there was one. Here it is. At this point in time, we're allowing for the possibility that it might be there. We're also allowing for the possibility that there's another fraction that has a constant numerator that only has that linear factor to the first. And in fact, we know if there isn't one of these fractions, what will A turn out to be?
0.
It'll be 0. So that's a possibility. So we allow for the possibility that that fraction is there, even though in reality it is not there. And if that's true, A will turn out to be 0. Yes, Chandler.
So if you were to have like x plus 4 raised to the 4th,
Yes.
you would have to account for
Yeah. And
a
we'll-
over,
Yep.
yeah, 1, 2, 3. Okay.
Right. You'd have 4 different possible fractions that could be there, and we'll account for that term to the first, that linear factor to the second, linear factor to the third, linear factor to the fourth.
Okay.
So basically, we account for all those denominators till we reach the highest degree of this linear factor, and then we also allow for a third factor constant over the other linear factor. All right, what's the next process? Let's at least get down what our next step would be, and then we can pick up from this point tomorrow. Okay. We need a common denominator. Left side, you'll never have to mess with the left side as far as changing it. So this ugly rational expression that we started with in the integrand, leave it alone, and now we need a common denominator. What does that here?
X plus 4 and x minus.
Okay, we need 2 of those factors. What do we need here?
X minus 2.
Isn't this kind of the same thing we did earlier, but we knew the numerators? Now we don't know the numerators because that's how you really start the decomposition. And x minus 2 needs an x plus 4 squared numerator and denominator. So let's write down this step, and then we'll reconvene tomorrow. Everybody agreed the denominators are now the same?
Yes.
Yes? So we can add the numerators together. So we've got A times that, B times x minus 2, and C times x plus 4 squared. Yes, Brendan.
X plus 4 for A.
Well, we don't know what A is.
Okay.
A is going to end up being 2, but we don't know that yet. All right, so we will pick up from this point on this problem tomorrow.